Hey guys, welcome back to the Kubernetes series. Once an application is scheduled onto a node, it starts consuming node resources. And it's not just one application that gets deployed to Kubernetes cluster. So we should be extra cautious when deploying our application to Kubernetes such that our application uses computing resources like CPU and memory wisely and our application performs well and doesn't impact other applications. In this chapter, we will learn how to make sure our application gets guaranteed resources using requests and also how can we restrict memory for an application using limits. Also, we will try to understand what quality of service is and set a minimum, maximum and default resources per pods in a namespace using LimitRange. And finally, we will learn how to limit the resources in a namespace using ResourceQuota. And needless to say, we will learn everything with complete hands-on. So without any further delay, let's get started. Before jumping in, let us try to understand few things about computing resources. Every node has resources like CPU, memory, and disk space. CPU and memory are called compute resources. We can request these compute resources from a node for later use. CPU is measured as a fraction of time. For example, 200 millicores are 1 CPU, which is equivalent to 1000 millicores. CPU is a compressible resource, meaning whenever an application is using maximum CPU, it is throttled, meaning it cuts down the CPU cycles and slows down the response rate instead of killing the process. One CPU is equal to one virtual CPU in AWS, one core in GCP, one virtual core in Azure, and one hyperthread on bare metal. And the data that the processor is using currently is stored in the memory and it is measured in bytes. 1 kilobyte is equal to 1000 bytes and 1 kibibyte is equal to 1024 bytes. The same applies to 1 megabyte and 1 mebibyte. Unlike the CPU, memory is not compressible, meaning once a process is given a chunk of memory, that memory can't be taken away from it until it's released by the process itself. And when a process uses maximum memory, the process will be killed. These computing resources like CPU and memory are very important and a node, and we should be extra cautious while using these resources. Let's say we have an application and it needs minimum CPU and memory to start. For example, 1 CPU and 200 megabytes memory. If this application is deployed onto a node where enough resources are not available, our application may not start. What if there is a way to instruct Kubernetes to deploy this application or pod onto a node that has minimum capacity? For every container, we can define the resources and we can request Kubernetes to deploy this application onto a node where minimum CPU and memory are available using requests. When we define the request, Kubernetes will guarantee to schedule this pod onto a node where the minimum capacity is available. Now this pod uses the node 2 resources immediately after scheduling and the allocatable resources on node 2 changes to 400 megabytes and 200 millicores. In any case, if there are no nodes with minimum capacity defined in the pod lies in the pending state until the resources are available. Once the resources are available on any node, then Kubernetes scheduler schedules this pod onto that node. In short, Kubernetes compares the resource request defined in the pod to the available resources on each node in the cluster and automatically assigns a node to the pod. When we don't specify CPU or memory request, we indirectly mean that we don't care how much CPU time the process running in the container is allotted. In the worst case, it may not get any CPU time at all. Let's say all of a sudden there is a memory leak in the first application and pod 1 started using a lot of memory. What happens to the second application on that node, which is pod 3? It may get terminated as it gets less memory to use, which is not sufficient. If you could have instructed Kubernetes not to allow the pod 1 to use memory more than a limit, we could not have been in this situation. Luckily, Kubernetes saves us from this case too. In Kubernetes, we can instruct to limit the CPU and memory to a container. And this can be done with the limits in the same resources section. So to summarize both requests and limits, with request, we define the minimum resources that should be available on a node to schedule a pod, and with the limits, we define the maximum resources a pod can use. If we don't define requests and limits, the Kubernetes scheduler may schedule all our pods onto the same node without triggering any autoscaling, which will eventually make the Kubernetes node overloaded and unstable. And our application performance will suffer as the request will start throttling when maximum CPU is used, and our pods may be killed if there is not enough memory available. Let us see these requests and limits in action. Before demonstrating requests and limits, I would like to introduce to a tool which is stress. As we are dealing with CPU and memory, we need a tool that creates the load instead of writing so much of code to impose the load. With this tool, we can easily define how many CPUs can be used and how much memory should be filled out. Basically, we are simulating the CPU and memory usage in the pod. Here we are running the stress process which uses the 8 CPUs and 128 megabytes. Docker image is also available for this stress tool. When we use this image, our pod comes with a pre-installed stress tool. So let's create a pod. resources-demo-pod.yaml. So in the interest of time, let me paste the basic pod definition. Here we are using stress image that uses the 2 CPUs and 1 gigabit memory. So now let us try to add the request to this container. Resources, and in that request, so let's define the CPU as 1 CPU and memory as 10 gigabytes. So here we are instructing to Kubernetes that please schedule this pod onto a node where at least 1 CPU and 10 gigabytes memory is available. So let us try to apply this pod. Before that, let us try to list down the nodes of the cluster. Kubectl get nodes. Now we have one node with the name minikube. Let us try to describe this node. kubectl describe node and node name. As you can see, 8 CPUs can be allocatable and also around 8 gigabytes memory is allocatable. But we requested around 10 gigabytes of memory. So the expectation is this pod should not get scheduled onto any node as there is no node with a minimum of 10 gigabytes memory available. So let us try that. kubectl apply -f resource management -demo -pod.yaml. As you can see, the pod is created. Let us try to look at the status of this pod. As you can see, the status is pending. This pod never gets scheduled as there is no node with that memory available. Let us try to change the memory and see if it gets scheduled. Let's change it to 2 gigabytes. Go back to the terminal and apply. Oops, some error. Let us see what the error is. The error states that we cannot update the fields other than this. So once a pod is created, we are not allowed to change the resources. So let's delete this pod and then change it. kubectl delete pod. So now let's apply. As you can see, the pod is created. Let's list down the pods. As you can see, the container is getting created, meaning a node has been assigned to this pod and the container is creating. Let's try to look at the status again. As you can see, the pod is running on minikube node where we had around 8 gigabytes memory allocatable. We can check how many resources a pod is consuming with kubectl top pods. The error says that metrics API is not available. The kubelet on each node collects metrics such as CPU and memory from our pods, and the metric server collects and aggregates metrics from all kubelets. So the kubectl top command consumes the metrics exposed by the metric server through API server. So we need to enable the metric server in our cluster to check the pod resource consumption. By default, metric server is already enabled in many clusters like EKS. In minikube, we can enable the metric server with minikube add-ons enable metrics server. As you can see, the metric server add-on is enabled. You remember, we discussed about add-ons in the English chapter of this series. Now let's run the same command. As you can see, this pod is using around 1850 millicores, which is around 2 CPUs and 1026 megabytes, which is around 1 gigabyte memory. This is because we are creating that load with the stress tool. Now this pod can use as much as CPU and memory. There is no restriction at all. But if there are other pods running on the same node, those pods will be impacted because of this limitless usage. So it's always a good idea to compute the resources for your pod and define the limits. We can define the limits with limits same CPU as 2 and memory as 3 gigabytes. With this limit, we are instructing Kubernetes that do not allow this pod to use more than 2 CPUs and 3 gigabytes memory. So intentionally, let's impose the load of 4 gigabytes, which is more than 3 gigabyte limit, and see what happens. Let's go back to the terminal and delete the pod, kubectl delete pod name, and create the pod again with the kubectl apply. As you can see, the pod is created. Let's list down the pods. As you can see, the status is OOM killed, which means out of memory killed. This is because we limited our pod to use only 3 gigabytes memory, but our pod is using 4 gigabyte memory, which is more than 3 gigabytes. And as we discussed, memory is not a compressible resource, meaning if the pod uses more memory than the limit we defined, the pod gets restarted based on the restart policy. We discussed about the restart policy in detail in the last chapter of this series. So let's change this limit to 5 gigabytes and change the CPU limit to 1 CPU. So in this case, we are limiting the CPU to 1 CPU, but we are imposing 2 CPU limit. Now let us see what happens. Let's delete the pod and create again. The pod is created. Now let's list down the pods. As you can see, the pod is running. It's not killed even though we cross the CPU limit. With this, we can conclude that when our pod uses the CPU more than the limit we defined, the CPU is throttled. But when our pod uses the more memory than the limit we defined, the pod will be killed and restarted. And please note that we define this request and limit at the container level, not at the pod level. When we have multiple containers in a pod, while scheduling, all container resources are summed up and will be compared against the node resources available. So by configuring these requests and limits for the containers, we can make efficient use of CPU and memory resources available on our cluster nodes. Even after adding the resources in our pod definition carefully, because of some reasons, our pod may use more CPU and memory than our limits. No problem with the CPU as it throttles, but the problem is with the memory because it will be killed. Let's say we have a node with 8 gigabytes memory and we are scheduling 2 pods with 3 gigabytes each. Now we are left with 2 gigabytes unallocated memory and our pods are using less memory than we requested. So now we have 3 gigabytes of memory free on our node. Now if we try to schedule another pod with 3 gigabytes minimum memory, the pod doesn't schedule even though we have 3 gigabytes free memory on our node. Please note that Kubernetes scheduler looks for the unallocated resources while scheduling the pod, not the free memory. And let's say we define the limits more than the node memory, meaning we can schedule our 2 pods with 6 gigabytes limit each. Kubernetes scheduler still accepts it because it looks at the request while scheduling, not the limits. This is called overcommitting state as the pods are scheduled with the limits more than the node capacity. Now let's say all of a sudden our pod 2 started using full memory, which is 6 gigabytes, which is equal to the limit that we defined on the pod 2. There is no problem as it is not exceeded the limit. But both pods collectively using the 9 gigabytes of memory, which is more than the node memory. Now one of these pods should be killed. Now which pod should be killed is the question as both pods are within the limits. There is no mistake with any pod here. But our Kubernetes is very smart. Kubernetes decides which pods to kill by categorizing the pods into 3 classes, more specifically quality of service class. We don't set this class to the pod. Kubernetes automatically assigns this class to a pod based on the request and limits we defined. When we don't define both requests and limits, Kubernetes assigns best effort class to the pod. Please note that this applies to both CPU and memory. And as we are not giving any resources, when other pods needs more CPU or memory, this pod might not get any resources. And when no other pod is deployed onto the node, this pod can use as many resources as it needs. So if Kubernetes needs to decide which pods to kill, Kubernetes deletes the pods with best effort quality of service class. Because when we don't set requests and limits, Kubernetes assumes that we are not much bothered about this pod and it can kill these pods when there is a need. And when we define the requests and limits and they both are equal, the Kubernetes assigns a guaranteed class to the pod. Note that this must be true for all containers in the pod. Pods with this class are guaranteed to get the requested resources. All other pods like request and resources are not equal fall into the burstable category. So in short, when the system is overcommitted, the quality of service class determines which pod should be killed so the freed resources can be given to the high priority pods. Pods with best effort class are killed first, followed by the burstable pods and finally guaranteed pods. We can check a pod's quality of service by describing the pod. So kubectl describe pod name. So as you can see, the quality of service class for our pod is burstable because we define the both requests and limits, but they are not equal. Kubernetes gives us fine-grained control over resources. Sometimes if administrators want to control how many resources a pod can use maximum or want to impose the default requests and limits if they are not defined, Kubernetes provides us with another resource which is limit range. For example, after we create a limit range, when we try to schedule a pod with 20 millicore CPU, it will not be scheduled as we define the minimum CPU for a container should be 20 millicores. If we change it to 100 millicores, it works as it lies between minimum and maximum. Not only that, when we don't define requests or limits, limit range will set the defaults automatically while creating the pod. Let's see this in action. Let's create a new manifest. LimitRange demo.yaml. In the interest of time, I'm just pasting the limit range object. So here we are applying the limits with the limit range resource. And these limits can be applied at the pod level and container level and finally at the persistent volume claim level also. So here we are defining that the minimum CPU should be 50 millicores and the minimum memory should be 5 MB. If we create a pod with less than these requests, the pod will be rejected. And same applies to the maximum. If we try to create a pod with the limits greater than these maximum limits, it will be rejected. So the same applies at container level. And also, if we don't define the request in the pod, the default request will be applied. And also, if we don't define the limits, the default limits would be applied. This max limit request ratio defines that CPU limits will not be allowed to be more than 4 times greater than the CPU request. Same applies to the memory. We can also define how much storage a PVC can claim. For a detailed understanding of the persistent volume claim, please refer to the volumes chapter of this series. So let's apply this. kubectl apply -f LimitRange demo.yaml. So let's apply this. Now let us try to create a pod more than the limit and see what happens. So let's change the CPU from 1 CPU to 10 millicores and try to create the pod. So let's apply the pod. As you can see, there is an error. The error is the minimum CPU usage per pod should be 50 millicores, but we requested 10 millicores. And also, maximum memory usage per pod should be 2 GB, but the limit is more than that. So like this, we are crossing so many limits for this pod. So if we fix all these limits, the pod will be created or else the pod will be rejected. So this is a homework for you to fix all these errors. Limit range validates each pod in the namespace, but sometimes we want to restrict at namespace level instead of pod or container levels. We can achieve this with ResourceQuota. With ResourceQuota, we can restrict the requests and limits at namespace level. Not only requests and limits, but also number of pods, number of services, number of deployments, etc. Let's create a new manifest. ResourceQuota demo.yaml. So again, in the interest of time, I'm just pasting the manifest. So here we are defining a resource quota where we are saying that in the namespace where this resource quota is being created, in that namespace, all the pods should not be using more than 2000 millicore CPU. Also, the memory should not be exceeded more than 8 GB memory. Also, we are saying that the maximum number of pods that can be created is 10 and the replication controller should be 5, and so on with the other Kubernetes resources. And also we are saying that only 2 PVCs can claim storage with SSD storage class. So like this we can apply the limits at namespace level. Let's save it, go back to terminal and apply kubectl apply -f resource quota demo.yaml. As you can see, the resource quota is created. Now let us apply the pod. As you can see, there is an error saying that we requested 1 GB memory, but the maximum request that we can make in a namespace is limited to 200 MB. This was defined in the resource quota. Now let's go back to the pod and change the memory from 1 GB to 200 MB and go to terminal and apply the pod. As you can see, the pod is created. So this way we can restrict the requests and limits at namespace level. That's it for this chapter. I hope you liked it. My name is Pavan Elthepu and I thank you very much for watching this video. If you liked it, please share it with your friends and do not forget to subscribe to my channel to not miss any updates.